Okay, page 195 is where we're kind of starting, and we have a learning goal there. And the learning goal is to use Avogadro's number to calculate the number of particles in a given number of moles, to calculate the number of moles of an element in a given number of moles of a compound. So within this section, 7.1, we're just determining what Avogadro's number is and how we can use it in which to calculate moles in general and calculate moles within a compound. So they use as a comparison, when they do this, they use as a comparison dozen and a ream and a gross and what those units represent in counting. So a mole is a count. So if I put 1 dozen here, we know that count is how much? 12. Right. If I put 1 ream here of paper, if I have a ream of paper, how much is that? 500. Okay, it's in there. Okay. If I have 1 case, we got 24. So it's a way of counting that you can count in multiples of 12 or 500 or 24, depending upon the size that you're counting. So if I just put up here a value that's 480, let's say 480 pencils or pens, how many dozen of pens do we have? 40. Okay? So some of you guys could figure that out because you know that 12 has to be divided into 480 in which to get your number. So then you would have 40 dozen. Now, to set that up, you would do, if being a chemist, I would go, well, show me how that works out. And then you would go, well, there's 480 pens in total. And I know when I convert that for every 12 pens, I have 1 dozen of pens. So when I divide it out, I get 40 dozen. Any questions with that? Pretty easy, right? Yeah. Okay? Well, when we deal with Avogadro's number, it is a big number, and the reason why it's so big, it takes that many in which to make up these weights on the periodic table. So when you look at the periodic table, you're going to have weights. They're called atomic weight. And when we take a certain number of atoms of a particular element, and we count them, and up to a certain point, we'll count them up to a certain value, which is Avogadro's number, we get these weights here. Okay? We get those weights. So let's just do another real simple example. Okay? So that you can... I will tell you this. Some students don't like to be detailed in their setups. And then they struggle. They might not struggle right away. Like some of you were able to go, oh, that's 40. Because you go in your head, 12 goes into 48. 4 times into 0. Okay, that'd be 40. You can do it that way. But we're going to have multiple steps that we'll deal with. So if you get bad habits now, when we get tougher and longer setups, you're going to not get them right. Okay? So what I would tell you to be successful is to be as detailed as you can. Okay? Even though it takes a little bit more time to do that, especially if you have not been doing well at the math, be really detailed. Detail really helps you out because units kind of tend to cancel out, and whatever you have left over in your units, that's your answer. Okay? So let's say that we have 2,500 pieces of paper that we need to run off in which to give out to, the community or something, but we need at least 2,500 papers. So how many ream would that be? 5, right? Because 2,500 paper If we have 500 papers that equal 1 ream, and that would be, if you go around to some of the copy rooms and that, they'll have a encased about that thick a paper, and that's 500. Okay, it's called a ream. So then you say for every 1 ream, and then of course that would be 5. So let's translate that to what's called Avogadro's number. Okay? So Amadeus Avogadro he was a Italian physicist that kind of came up with a number that's really huge. This number is so big that if you tried to count up to that number and that quantity right now, 24/7, 365, in 100 years, you would not count that number. You would not have enough in your count to reach that number. If you look, another thing that you can look at, if you look at an apple and you put the size of an apple and you shell out the earth to where you're just putting things in the earth that's void of anything, it would be about that number of apples that would fit inside the earth. Okay? Another analogy, I don't know how close they are, but it just tells you a big number. If you take a drop of water, and then you would count how many drops of water are on all the oceans of the world, it's that number. Okay? So you think, big number, right? And so this number is 6.022 times 10 to the 23rd is what it is. All right? So it's this number right here. Okay, that's the number. Now, these are all estimates. Okay, I probably could have put the 2 here next to the 2. A lot of times I use just 6.02. So this is the number, okay? These are all estimates right here. These zeros are, we could take it out a little bit further, but most of the time we don't have to take it out beyond 4 digits because most of our measurements are not going to be beyond 4 digits. They're going to be just 3 or 4 significant digits that we have to deal with. So that's why I kind of limit it to 3, but that's what that number is going to be. Okay? So definitely want to use scientific notation. We've been using that quite a bit. If we have 1 mole of particles, and I'll tell you what these particles are here later. We have 1 mole of particles. That's equal to 6.02 times 10 to the 23rd particles. So what's a particle? Well, our particles are really, really small. We can't see them. Can't see them with a regular light microscope, electronic microscope. They're even tough to focus on and look at. So particles could be such things as atoms. Could be such things as molecules. Could be formula units. I'm going to tell you the difference between a formula unit and a molecule. A molecule is when you've got nonmetals bonded together. Just for your information. And a formula unit are ionic compounds. So we don't say molecules of NaCl, because NaCl does not form a molecule. It forms an ionic compound. So we'll say formula units of NaCl. Okay? If we say carbon dioxide, we'll say a molecule because they're both nonmetals. So that's just for your information later on to understand a question on a test. So it says how many formula units would you have of MgCl2 or magnesium chloride? You realize that's what you have to state for that. And then also we could have ions. in there too. So atoms, molecules, forming units, ions. We could actually have electrons. We can also count electrons. Okay? So those would be all what we do with particles. So we're going to start really easy, nothing real difficult to do. We're just going to do some conversions with this as our guide. Okay? So that's our guide, Avogadro's number. So then I'm going to go ahead and give you a problem. I'm going to say how many atoms of carbon is contained in 0.50 moles of carbon atoms. Alright, so this is a real simple, general question. We want to know how many atoms we would have based upon 0.5 moles of carbon atoms. So this is the only conversion that we have to deal with, because this up here can represent atoms and moles of atoms, because they're particles. So setting up this problem, how would we set it up? What would we do in which to do our show our work? What would have, this is a conversion, so what do you think goes out in front of our conversion? 0.50 moles. That's my sample size. This is my conversion. You guys remember, conversions usually is one value over another. And you don't start with that, right? You start with your sample size. So my sample size is 0.5 moles. Okay, I'm going to be real detailed. If this is moles of carbon there, what do you think has to go down here? Moles of carbon, right? You're going to find out whatever you start out with is your first division, units. So right away you can write, and I didn't put any numbers in there. Sometimes you guys get in too big of a hurry and you start putting numbers in. Put your units in first, okay? Then you can always substitute in your numbers later based upon what it is up above in your conversion. So I want to find atoms of carbon. So then up here I'll go atoms of carbon. And there's moles of carbon. So what numbers go in these two spots? How about for the mole? What goes in that spot? 1 mole. Okay? So this is 1 mole of atoms. And this is the total number of atoms. Okay? Now if we're talking about ions, it'd be moles of ions. If we're talking about molecules, it'd be moles of molecules. Just like dozen. So down here we'd say for every 1 mole, I've got 6.02 times 10 to the 23rd. You can take it out further. If you want to put 6.022, you can. So I multiply 0.5 times 6 is what? 3. 5 times 6 would be 30. But so that would be 3.01 times 10 to the what? What would be my final answer? Yeah, but I need to... What's my exponent? 23rd. Everybody see that? And that would be atoms of carbon. Any questions? Does that make sense? See, my units will always tend to divide out. Dividing out in chemistry is really huge. Knowing what divides out and what you can't divide out. So that would be my answer, and that's how many atoms I would have. Okay, let's do another one and do it the opposite, where I'm giving you the number of atoms and you got to find moles of atoms, because that's the most of the time that's what you do. I don't do very many of these problems where we have you use the scientific notation. We really, tomorrow is what we're going to use a lot, and that's moles and grams comparison. And we'll explain why we can compare them that way. But we don't really want to deal with atoms in a count. We'd rather deal with moles, and then we usually do moles and grams. So we'll do a few of these, but this isn't a huge part of what we're going to do in chemistry right now. Okay, the conversions would be, but that would be about it. Okay, so next question would be, how many moles of aluminum atoms is contained in a sample of 1.2 times 10 to the 24 atoms of aluminum. So now we just want moles, and moles are much easier to work with. They're common numbers. You're not going to have big exponents with moles, okay? Usually 97% of the time they're just going to be basic, simple, small numbers, okay? Nothing with exponents. Moles won't have exponents usually, a lot of times. If they do, they're really small exponents that you'd have with that. So how would we set this one up? We'd say 1.2 times 10 to the 24th atoms of aluminum. And then we go, see, I'm being very detailed. So then what unit goes down below? Atoms of aluminum, right? And then what unit goes above? Moles. How many moles? So then moles of aluminum up here. So down here goes 6.02 times 10 to the 23rd. And up here goes 1 mole. So 1.2 divided by 6 is what? 0.2 times 10 to the, so it's 24 minus 23. 1, right? So times 10 to the first. So if I would rewrite that, what would it be? 2. So that would be 2 moles of aluminum atoms. Okay? And that's all you do. So I have 2 moles of aluminum atoms. Okay, this next part won't take too long. Make sure you're showing your units cancel. Be very detailed. The more detailed you are, the better you're at. Students that are detailed really do well in this section. If you're not detailed, then you kind of do things your own way and don't put units in, and that gets you into trouble. Okay, so we're going to count atoms. Counting moles of atoms in a compound. So we're gonna deal with some compounds now. Now that we just dealt with single elements like aluminum and carbon, now we're going to do counting moles in a compound. So let's say that we have a compound and we have 1 mole of molecule of C6H12O6, which is glucose. So then, let's say that we want to count how many moles of carbon we would have, moles of hydrogen that we'd have, and moles of oxygen that we have. So now what we need to do is we need to individual count. So if I got 1 mole of molecules, and I know I got 6 carbon atoms for every molecule, how many moles of carbon do I have? Okay, it's really pretty simple. If I have 1 mole of molecules, Okay? You can think of this. If I have one car, how many tires do I have on that car? 4, right? Okay? If I have a V8 engine and I have a car, how many spark plugs do I have in that car? 8. Okay? Right? Makes sense? So, if I have 1 mole of molecules, how many carbons do I have? 6. How many hydrogens? 12. How many oxygens? 6. Okay? Now, if I had 2 moles of molecules, like 2 cars, how many tires would I have? I have 2 cars. 8. Okay? So if I had 2 moles of molecules, how many would I have of carbon? 12. It's just multiplied, right? Yep. So, counting atoms, this is really simple. Let me give you one to practice that's not a whole number, and then you can tell me what you guys think on my count. So I'm going to say I have 1.2 1.22 moles of this compound. Okay, so how many moles of lead do I have? So moles of lead, moles of phosphorus, and moles of oxygen. So the first one's the easiest one. How many do I have? 3.66. Okay, I take 1.22 moles of that whole compound, and then I go for every 1 mole of that compound. I usually write it out. I'm not going to. I have 3 leads. It's a ratio. So it'd be what? 3.66, right? Okay. How many do I have of phosphorus?
488.
Okay.
4.88.
Yeah, first thing you need to do before you multiply by 1.22 is to figure out how many phosphorus you have. So this 4 multiplies through everything in there. So I got 4 P's. So be 4 times 1.22 would be 4.88. Okay, and the last one, how many, now before we multiply, how many do we have? Oxygens? 16. So how many moles of oxygen do I have? Somebody calculate that for me. 19 point what? Questions? All right, I got 2 problems for you guys to do tomorrow, and there's like 8 total in each. So page 198. Put these in your notes. 7.4 and 7.8 for Tuesday. Okay? So 7.4 and 7.8 for Tuesday. Remember, you retaking, you need to show me. You need to show me your page 191, 82, 80, 84, 90. Solve some of those. You guys don't have to solve them all. Like, I'm going to give you flexibility. If you missed all of the bottom ones because you weren't able to write the formulas out, just do the problems up there dealing with writing formulas from the names. Okay? If you had trouble with just Roman numerals, okay, just do the ones that have Roman numerals in it to where you got to write the formula. Okay? I'm not asking you to do every single one of them. Now, if you missed some of both, or a bunch of both, then it's probably good that you do all of that. Okay? And then make corrections on your test as well. Okay? All right, you got the rest of the time to work on that.